Hi there. My name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. In the last lecture of ECE2026, Introduction to Signal Processing, we computed the Fourier series coefficients for a square wave. In this lecture, we'll do the same for a triangle wave. We'll compute a triangle wave defined like this. Once we compute the Fourier series coefficients, we can compute the Fourier series coefficients for a triangle wave centered at a different point, perhaps like this, by using the time shift property we talked about in the previous lecture. Remember that A0, the DC coefficient, is going to be the average of the waveform over a period. So it's the signed area of the waveform divided by the period. And a little bit of thought will tell you that that should be 1/2. If I think about this triangle here, well, that would have an area of T0 over a fourth. If I add another triangle like that, that gives me a total area of 1/2 T0 divided by T0 gives me a half. Or it's pretty easy to tell this waveform is centered around a half on the vertical axis. Now, you need to be careful in interpreting this formula. It's only valid for this region. We understand that the formula is useful in this region, and then outside of that region, that form is replicated. I'm going to start this lecture by showing you the answer, and then we'll go through the derivation of the A sub k. Notice that the even harmonics are missing. We saw that that was also the case for the square wave. The odd coefficients are given by -2 over pi squared k squared. These slope off fairly quickly on the order of 1 over k squared. This is in contrast with the square wave, whose coefficients sloped off on the order of 1 over k. For both the triangle and square waves, the missing harmonics result in something of a hollow sound. In music synthesis, the square wave might be the start of something like a clarinet sound, whereas the triangle wave might form the basis of a flute sound. So here's the derivation of the A sub k. I'm not going to go through every single detail here. You can pause the video and look it over. I just want to point out a few specific things. Remember that this formula is only valid in the region minus T0 over 2 to T0 over 2. So that's how I'm going to define my limits in my Fourier series analysis integral. To keep the notation compact, we're going to write 2 pi over T0 as omega naught. You don't have to do that. We're doing that here because these symbols are getting kind of small and difficult to read, and we don't want them to get any smaller. Now, you can't really evaluate an integral of something that has an absolute value in it directly. You have to split it up into the regions where the argument to your absolute value is positive and the regions where it's negative. Now, I can take the 2 and the T0 and pull those out in front. That leaves me with this T, but I need to split it up. So in the area where T is positive, going from 0 to T0 over 2, I just write T. But for the area where T is negative, to take the absolute value, I need to write minus T. So that is for the region going from minus T0 over 2 to 0. So taking this minus sign and pulling it out in front, we see that we need to compute this indefinite integral. You can compute this using integration by parts, or you might find it in a table somewhere, or you might just ask Wolfram alpha. Anyway, using that form and plugging in the limits to compute the definite integral, you wind up with this monstrosity. Let's copy that monstrosity to the top of the next slide. At this point, notice we have a lot of these omega naught T0 combinations. Well, omega naught times T0 is just 2 pi. So I wind up with this e to the j pi k and this e to the minus j pi k. These are 1 for even k and -1 for odd k. So we'll rewrite these exponential forms as -1 to the k. Then doing a bit of algebra, we can reduce that form to this and wind up with this final answer. If you would like, you could grab a piece of paper and a pen or pencil and pause the video here and work through all of this algebra and double check it. But I would understand if you felt like you had more enjoyable things to do. Let's experiment with the Falstad Fourier web app. Notice that for a square wave, I need to put in quite a few harmonics before it really starts to look like a square wave, particularly because of that discontinuity. But when I switch to a triangle wave, I don't really need that many harmonics because they slope off so quickly. Now, while I have the app open, let's go back to the square wave and let's compare this to a sawtooth wave. The sawtooth wave has harmonics that slope off on the order of 1/k, like with the square wave, but it has even harmonics in addition to the odd harmonics. This will give it a buzzier, brassier kind of sound than the square wave. The square wave, triangle wave, and sawtooth wave are common waveforms in analog music synthesizers.